So it's exactly precisely the time to switch to the second talk. David Wajc. Okay, I pronounce your name correctly or not? You're not satisfied with that?
Yeah. Not satisfied. Wajc.
Wajc, okay. Maybe you can share the whole screen, then it will be less blurry. You're sharing the whole screen? No.
Yeah. Actually leave center mode in that case. Oops, sorry. Okay. Right. So shall I start?
Yeah, David will tell us about online edge coloring. Go ahead.
Thank you, Yossi. So as Yossi said, my name is David Wajc, and I'd like to tell you about tight bounds for online edge coloring. This is a joint work with Ilan Cohen here on the left and Binghui Peng here on the right. Now, strictly speaking, these affiliations are a bit out of date. So right now, both Ilan and I are unaffiliated, but don't worry, we'll land on our feet. Ilan will be joining Bar-Ilan University as an assistant professor in about a month, and I'll be starting a postdoc at Stanford tomorrow. All right, so let's talk about some math. So the problem we'll be studying today is the edge coloring problem, where I remind you a k edge coloring of a graph is an assignment of one of k possible colors to the edges of the graph, such that each vertex is most one edge of any given color. Okay, so for example, here this painter has 6 edge colored this graph. If we were to change the color of the rightmost pink edge to green, this would not be an edge coloring since V has 2 incident green edges. All right, so it's trivial for any M edge graph to M edge color the graph by assigning a distinct color to each edge. And the natural question is, what's the minimum number of colors you can use to color this graph? What's the smallest possible palette? And as it turns out, the number of edges of the graph is not the right measure, but actually a graph parameter which is more tightly related to the problem is the graph's maximum degree, which will be denoted by delta throughout the talk. So why is this related? Here's an obvious first observation. If you want to edge color a graph, you need at least delta colors, because every node must see distinct edges incident on it. On the other hand, for bipartite graphs, this is actually sufficient, and we can even compute a delta edge coloring in nearly linear time. For general graphs, this is not the case, and it's actually NP hard to determine if a general graph is delta edge colorable due to a classic result of Hollier from the 80s. On the approximation algorithms front, we can actually get a +1 additive approximation by the classic theorem of Vissing's from over half a century ago, which says that every graph has a delta +1 edge coloring, and this can be computed in polynomial time. Well, on the topic of algorithms, let me briefly mention the kind of naive strawman solution for this problem, which is the greedy algorithm. Now, this algorithm inspects edges in some arbitrary order, and when inspecting an edge, assigns it the lowest feasible color, which is compatible with the previously chosen incident colors. So if you think about this for maybe 10 seconds, you'll convince yourself that this is a 2 delta -1 edge coloring algorithm. And actually, the proof is very simple. Here's a proof by picture. When I consider the edge UV, U is used at most delta -1 colors, V is used at most delta -1 other colors. So all in all, the view is 2 delta -2. So one of the first 2 delta -1 colors is still up for grabs. Now, matching or sometimes surpassing the 2 delta -1 color bound of the greedy algorithm has been widely studied in all your favorite computational models. Of course, as you could guess from the title, I'm not going to tell you about any of these models, but instead I'm going to talk about online edge coloring. And in particular, I'm going to talk about online bipartite edge coloring, where the underlying input is a bipartite graph, initially unknown. What we do know are the nodes on one side of the graph. We'll refer to these as offline nodes. And what we're going to have revealed to us are nodes on the right side, referred to as online nodes, which arrive one at a time together with all of their incident edges. Now, what an online algorithm has to do when an online node shows up is to decide immediately and irrevocably which colors to assign these edges. So we'll color it like so, another node shows up, we'll color its edges like so, and so on and so forth. And as usual with online algorithms, our measure of success here will be the competitive ratio, which is nothing but the worst case ratio of all graphs and arrival orders of the number of colors used by the algorithm to the hindsight optimal, which in our case for bipartite graphs is just the maximum degree. Great. So just to make sure we're all on the same page, the greedy algorithm I mentioned from a couple of slides ago is trivially an online algorithm, and it's essentially too competitive, up to low order terms. And so our starting question for this project was, can we outperform the greedy algorithm? And unfortunately, a note published by Barnot et al. In '92 seems to indicate that this is not the case. Their note is simply titled, "The greedy algorithm is optimal for online edge coloring." Okay, this is shaping up to be a very short talk, but bear with me for a minute. So the natural question is, maybe you can, improve on the 2 delta minus 1 and at least improve the lower order terms. But as it turns out, they show that really greedy is the best you can hope for. So no online algorithm can even spare 1 color compared to what the greedy algorithm gives. Okay, bear with me. So if you inspect the lower bound of Barnot et al., you'll notice that this lower bound requires a number of nodes which is exponential in the maximum degree. So flipping things around and taking out logs, what this means is that this lower bound only holds for bounded degree graphs, for delta at most logarithm. And so what we argue is that you shouldn't be thinking about this lower bound as a 2x multiplicative lower bound, but rather you should be thinking about this as a plus log n additive lower bound. Right? The optimal bound is delta, and in an online setting, you can only hope to delta plus log n color the graph. And so the natural question is, can you do better if delta is super logarithmic? And it's actually such a natural question that even Barnot et al. Posed this question and raised the following conjecture. There exists a roughly 1 competitive algorithm for super logarithmic maximum degree. All right, so what do we know about this problem? So there's been partial progress made on this problem by Motwani and co-authors over the years. In Fox 03, Agarwal et al. Showed that you can indeed get a roughly 1 competitive algorithm for a large enough maximum degree, but here they needed maximum degree, which is super quadratic in the number of nodes, so naturally this only holds for multigraphs. Okay, for the remainder of the talk, we'll really be focusing on simple graphs. Improving on this, in Soda 10, Bahmani et al. Showed that you can actually beat the greedy algorithm for super logarithmic maximum degree, showing a 1.26 competitive ratio, but still bounded away from 1. Okay, so both of these kind of fall short of the conjectured bound, either in the approximation ratio, competitive ratio, or in the bound on the maximum degree. I should also point out that both of these results assume random order edge arrivals. So they assume some kind of help on the part of nature. In this work, we study adversarial vertex arrivals in the bipartite graph model I mentioned earlier. So somewhat incomparable, but these are the closest results to compare to. Okay, so what do we show in this work? So in this work, we get the first positive results for adversarial arrivals, for online edge coloring under adversarial arrivals. And in particular, we fully characterize the online bipartite edge coloring problem for the interesting super logarithmic maximum degree regime. So our first result is a positive resolution of the conjecture of Barnot et al., giving a roughly 1 competitive algorithm, assuming the maximum degree is known. Now you might be wondering if assuming that this maximum degree assuming that the optimum value, this maximum degree is known ahead of time is reasonable, or even if it's necessary. And as it turns out, it is necessary. And we show that if you do not know the maximum degree, no algorithm is better than e over e minus 1, or roughly 1.58 competitive. On the positive side, we show that even if you don't know delta, but you know that delta is at least super logarithmic, then the greedy algorithm is not optimal. And we can actually match the lower bound from result number 2, giving a roughly e over e minus 1 competitive algorithm for unknown large maximum degree. Okay, so again,
David, a short question. Anna is asking, are these results for general or for bipartite graphs?
These are, thank you, Anna. These results are both for bipartite graphs, or all 3 for bipartite graphs. Okay, so again, just to summarize, in this bipartite graph model, if you know delta up front and you know it's large, a roughly 1 competitive algorithm is the best you can hope for. And we can actually show that you need to lose a little order of 1 term. And if you don't know delta, the optimal bound is roughly e over e minus 1. Apologies for the noise outside. Good, so these will be a bit too many things to talk about in one talk, so I'll mostly focus on result number 1 and maybe briefly say a few things about results 2 and 3. Okay, so for the remainder of the talk, name of the game is, you know delta, you want to get a roughly 1 competitive algorithm. And just to get our feet wet, let's start with a warm-up problem, which is to offline delta color bipartite graphs. So our starting point here will be a classic theorem of Koenig's from over a century ago, which asserts that every regular bipartite graph contains a perfect matching. You might have seen this as a corollary of Hall's theorem or 1,000,001 other proofs, but Koenig was the first one to prove this. Corollary of the theorem, which is actually equivalent to it, is that regular bipartite graphs are delta edge colorable. And what I'm going to do now is give you an algorithm which, given the black box oracle access to the theorem, proves this corollary. And we'll use this general intuition later for our online algorithm. We initialize an uncolored graph. Initially, it's the entire graph. We haven't colored anything yet. And then for delta iterations, we compute a perfect matching in the uncolored graph, color it with a new color, and remove it from the graph. Rinse and repeat. Okay, so pictorially, this looks something like this. Here's our 3 regular graph. We compute a perfect matching, color it red, remove it, pick a perfect matching, color it green, remove it, so on and so forth. And after delta iterations, every node has lost 1 edge in each iteration, so we're left with no more edges. And so this gives us a delta edge coloring of our bipartite graph. Great, so natural question number 1, can we implement this algorithm in an online setting? And as it turns out, due to a result of Ilan Cohen and mine from Soda 18, implementing step number 1 is impossible to do in an online setting. And actually, so it's impossible to compute a perfect matching in an online setting, even if I tell you that the graph is regular. And if you think about this for a moment, this also rules out one competitive edge coloring algorithms for, say, regular bipartite graphs. So, okay, let's not despair. We can maybe still get some intuition here. So what this algorithm is doing is, in every iteration, it decreases delta U, so the uncolored graph's maximum degree, by 1. So every color decreases the max degree by 1. So this would give us a 1 competitive algorithm, and that's, as I said, too much to hope for. So instead, let's go for a roughly 1 competitive algorithm, in which case all we really need is to decrease the uncolored graph's maximum degree at the rate of roughly 1 per color, on average, of course. Okay, so how are we going to do this? A key ingredient for a positive answer to this question is the following positive result from the aforementioned Soda 18 paper, which states that there exists an online algorithm, which I'll call marking D, which, if the parameter D is greater than the maximum degree, outputs a random matching M, which matches each edge E with probability roughly 1 over D. Okay, so I'll give you some corollaries in a second. I'd just like to point out this approximately equal is going to hide multiplicative 1 plus minus little order of 1 term, so factors, so I don't clutter the slides too much. Okay, so why is this algorithm useful in the context of decreasing the uncolored graph's maximum degree? If you run this algorithm and you consider any vertex of degree roughly D, then this vertex will be matched with probability roughly 1. So notice that here the union bound is tight. If you think of inclusion-exclusion, M is a matching. I'll never match 2 edges of a particular vertex, 2 edges or more. So each edge is matched with probability 1 over D. There's D of these. I'll match this vertex with probability D times 1 over D, which is 1. Okay, so this seems to be somewhat useful for our general agenda of decreasing the maximum degree. So let's see how we're going to use this. So our high-level approach is going to be as follows. For delta iterations, we're going to run this algorithm marking D on the uncolored graph U, where we pick D to be roughly the uncolored graph's maximum degree. So as I argued in the previous slide, this means that every vertex should have its degree decrease at the rate of roughly 1 per color. And so after delta iterations, the uncolored graph's maximum degree should be little order of delta. And now all we really need to do is just run the greedy algorithm on the remaining uncolored graph for like a cleanup stage, requiring another little order of delta colors. So all in all, delta plus little order of delta and a roughly 1 competitive algorithm as we want. Okay, so this seems nice and easy, but if you're looking at your timer, you might guess that this is a bit too easy. So here's a few problems with this approach. So problem 1 is that we don't know the maximum degree of the uncolored graph in an online setting. So when node number 1 shows up, really, I mean, there's a sequence of these uncolored graphs, right? The uncolored graph after removing 1 color, after removing 2 colors, 3, etc. And when node number 1 shows up, we have no idea what the uncolored graph of the 100th uncolored graph is, because this depends on future arrivals and future random choices of the algorithm. So this seems a bit problematic. And another problem, which maybe wasn't clear from notation, is that what we're saying about nodes degree decrease is that it decreases at a rate of 1 minus little order of 1, but this little order of 1 is not 1 over poly n, so we can't union bound and argue that the maximum degree decreases at the right rate. We don't have high enough probability. Okay, so sidestepping both of these issues is the following approach which we use. Instead of picking d to be exactly or very close to the maximum degree of the uncolored graph, we're going to change d periodically. So we'll divide our delta iterations into periods of a certain number of iterations, which I'll specify shortly. At the beginning of a period, we're going to have d, which is roughly the maximum degree of the uncolored graph. And then kind of the secret sauce is to pick the length of the periods to be just right, not too long and not too short, as Goldilocks would say. In particular, we don't want it to be so short that we cannot argue anything about the degree decrease of the uncolored graph. And we don't want it to be so long that degrees start fluctuating quite a bit and d is no longer a good estimate on the maximum degree.
So David, one more question from Anna. It seems like it's an offline algorithm, but I guess you'll refer to it later.
Yeah, thanks, Anna. So I'll actually only refer to this as an offline algorithm. The online implementation, I'm happy to talk about maybe in the questions part, but for now, let's just analyze this as an offline algorithm. If you want kind of a feel for why this is online, well, this algorithm marking d is online, and that's kind of all I really need. Okay, so let me substantiate what I said about these this not too long, not too short, just right. So we're going to take periods to be short enough that degrees don't really decrease during a period, since we're only removing a small number of edges from every vertex. And so in particular, our estimate of the maximum degree of the uncolored graph remains a pretty good estimate, and every vertex has essentially the same degree. Consequently, all the high degree nodes at the beginning of a period remain high degree nodes during the period. And so there are, for every color, there'll be match with probability roughly 1. And now if we take the periods to be not too short, or just long enough, then we can appeal to concentration inequalities and say that the uncolored graph's degree decreases in a predictable fashion. And so we can feed in this new value into the next period and just rinse and repeat. Okay, I think this was maybe a little abstract. Let me maybe instantiate this with an algorithm. So our algorithm is as follows. It's more or less kind of what we saw before, just a few more steps. So again, we're going to have this uncolored graph. We're going to have d, which is initially delta, and we're going to hope to maintain the invariant that this is an upper bound on the uncolored graph's max degree. And then our delta iterations, as I said, will divide into, say, root delta periods of root delta iterations each. In each iteration, we pick a new color. So step 0 is just some algebra saying this is a new color. We run marking d with this value of d on the uncolored graph u, color the obtained matching with a new color, remove it from the graph, rinse and repeat. So this is root delta iterations during a period. And at the end of the period, we decrease our bound d by roughly root delta. Okay, so we do this for root delta periods. And at the end of all of these periods, we just run a greedy cleanup phase. That's it. Okay, so what I'd like to do is convince you, maybe let me go back again. What I'd like to convince you is that this step requires little order of delta colors. Clearly the delta iterations require delta distinct colors. So really I need to convince you that at the end of these periods, the uncolored graph has bounded maximum degree, little order of delta. Okay, so how are we going to prove this? Well, the key lemma is as follows. If you consider a vertex v, which has degree roughly d at the beginning of the phase, and let's assume that d is sufficiently large at this point. So when I say it has degree at least d, I mean degree at least d in the uncolored graph at the start of the period. Then during this period, the degree decrease of v and u is roughly root delta with high probability. Okay, so basically what I'm saying is you're losing roughly 1 uncolored edge per color with high probability, and now I can take union bound and reason that this bound d here, can you guys see my cursor? Okay, thank you. So what I'm arguing is that I decrease d by roughly root delta, so d remains an upper bound on the uncolored graph. That'll be the corollary of this key lemma. Okay, how do you prove this lemma? So at the high level, it looks something like this. So during the period, since the period is not too long, the degree of V will remain roughly unchanged in the uncolored graph. So why is that? You started off with degree roughly D, and during the root delta iterations of the period, you've lost at most root delta edges in the uncolored graph. So D minus root delta, if D is sufficiently large, that's still roughly D. And now using the properties of marking D, which I'd mentioned a couple slides ago, what we get from this is that independently of what happened during the period up until a particular iteration of color C, vertex V will have an edge colored with colored C with probability roughly 1. Right? It has roughly D edges, each match with probability 1 over D, and never 2 at a time, so we'll match it with probability roughly 1. And at this point, if we pick root delta, if root delta is sufficiently large, say it's super logarithmic, then standard concentration inequalities and maybe a coupling argument shows that we actually lose essentially the expected number of edges in the uncolored graph. And that's it.
David, is it important to know the little o of 1? What is it? Is it exactly for the algorithm or it's not?
Not really. So I mean, this will be some polynomial term in log n over delta. But actually, also, I guess what I'm telling you here only works for delta at least log squared n. But you know, if you play with the parameters properly, you'll get the right bound. Okay. So again, every vertex that has roughly maximum degree loses essentially 1 edge per color during a period. And as a corollary of this, we find that, as I said before, D remains an upper bound on the uncolored graph's maximum degree with high probability until D is, say, roughly root delta, until D is little order of delta. As a consequence of this, since we have root delta of these periods, and in each one of these we decrease our upper bound D by roughly root delta, after all these root delta periods, the uncolored graph's maximum degree is little order of delta. And then, as I said before, the greedy algorithm at this point uses at most twice the uncolored graph's maximum degree, which is little order of delta. And from this, we obtain our main theorem. There exists a roughly 1 competitive algorithm for known superlogarithmic maximum degree. Okay, how are we for time? Good. So let me, in the following few minutes, briefly tell you about the secret sauce that goes into the unknown delta result. I'll give you a brief impressionistic picture of this. So first we start with a non-standard fractional relaxation of this problem. I won't go into the details, but here it is if you want to see the video later. For our lower bounds, we rely on prefix hardness and LP duality as first advocated for by Azav et al. I won't go into too many details about this here. For our upper bounds, we develop an optimal fractional algorithm and essentially show how to round this, well, something a bit more complicated, but show how to round this algorithm in an online setting using the online dependent rounding scheme, which underlies the results from the aforementioned SODA 18 paper. So in that paper, we really didn't state the dependent rounding scheme in its full generality. If you want to learn a bit more about this, I suggest you look at chapter number 5 of this thesis over here. All right, so let me conclude. So what we showed in this work was, as I said, the first positive results for online edge coloring under adversarial arrivals. And in particular, we fully characterize the online bipartite edge coloring problem for the interesting superlogarithmic case, showing some dichotomy between known and unknown delta. For known delta, the optimal bound is roughly 1. For unknown, it's roughly e over e minus 1, and both of these are tight. And I think these first positive results for adversarial arrival online edge coloring suggest a number of interesting open problems, and I'd like to maybe mention a few of these. So the first, so Anna was asking about whether or not these results hold for general graphs, and as I said, no, they only hold for bipartite graphs. It would be interesting to see if we can outperform the greedy algorithm in general graphs. So in this work, we show how to outperform it with a fractional algorithm. Unfortunately, our online dependent rounding scheme does not work for general graphs, so it's interesting to see whether or not it's roundable, or generally if you can get anything better than greedy for general graphs. A positive answer to this question would mirror a similar recent result of mine with co-authors in Fox19 for online matching. So there we showed that you can beat the greedy algorithm for online matching in general graphs. Another natural question is, can we do something for adversarial edge arrivals? So again, in this other Fox19 work, we show that for online matching, edge arrivals are strictly harder than general graphs, and in fact, greedy is optimal for this problem. And it will be interesting to see whether or not the same holds for online edge coloring, or somehow you can do something smarter for edge coloring under edge arrivals. Another question is, what can we show for random order edge arrivals? So we knew how to get the right competitive ratio and how to get the right dependence on delta, but can you do the best of both worlds? And as it turns out, the answer is yes. In recent work with San Battaglia and Fabrizio Gantoni, we resolve this question. So I guess it's not so much an open question, just kind of plugging in this new result. So you can get a roughly one competitive algorithm for super logarithmic maximum degree in the random order edge arrival model. Finally, let me point out that all the positive results known for online edge coloring are randomized algorithms, and the natural question is, can you do anything without the use of randomization? Okay, I think that's my time, so thank you. I'll open the floor for questions.
Okay, thank you, David. I see that there are couple of questions. So Mosen is asking, is the known delta setting, can one approach delta plus of log n or polylog n instead of the delta plus square root of delta log n, like improving the little of one, I guess?
Great. So the lower bound from the Soda 18 paper show that you cannot get anything better than delta plus root delta. And so it's not just a question of, particular algorithmic approaches. So root delta is really another additive lower bound. Whether it's possible to reach that is a great question. I don't know. So somehow getting like the right asymptotics in the little order of one is an appealing question. Also, strictly speaking, the lower bounds for randomized algorithms only hold for delta at most square root log n. And so I think there the problem is with the lower bounds, and really we should be able to show that the problem is hard for delta less than some log n term.
Mm-hmm.
But this requires some new ideas.
Okay, so Jason is asking a nice talk, David, which I agree. How do you manage with high probability concentration with square root of delta, which is about square root of n when delta is log n? Isn't it usually the log n necessary for concentration?
Right. So as I was saying, basically what I showed you in the slide works for delta super log squared n. If you really want to get the right bound, you need to say something like every period consists of, say, root delta log n, which will be super logarithmic if delta is super logarithmic itself. If that answers your question. If not, you know where to find me.
Okay, yes. And Yukio is asking, where do you use the assumption that delta is larger than log n?
Right, so this, I think, ties back to the previous question asked by Jason. Basically, I guess if I had more access to presenter view, I'd skip to that slide. So as I was saying, during a period, every high degree node is matched with probability roughly 1. So if the period is super logarithmic in length, you expect to be matched roughly, super logarithmic number of times. And then, And then by just standard concentration inequalities, you get what you expect, right? So here's where I'm using the fact that delta is super logarithmic.
Mm-hmm. Okay, and the last question is by Argurius, and he also thinks that it's a nice talk. And what if you know the delta in like there is a probability distribution over delta? Do you think that the problem become easier? I guess it depends on the model, but.
Interesting. So let's see, if we know distribution over delta. So I think the lower bound should probably say something about this. So let me maybe say a few more words about the lower bound. So the lower bound essentially says something on the lines of, if I give you the following promise problem, the input is going to be one of the following graphs, where these graphs are subgraphs of each other. So it's either this graph or this extension of this graph or a slightly larger graph and so on and so forth. Then if you try and hedge your bets against all possible stopping times, against all possible maximum degrees, then you're in trouble. And I think if you play with this, you should be able to say something also for distributions over maximum degree. Yeah, I mean, I'm happy to talk about this offline, but essentially I think this should tell you something about this question as well.
Okay. I think we are just done on time. Thank you, David, for the great talk. And yeah, let's continue.